session on transient response analysis. In the earlier two sessions, we concentrated on order of the system, different standard input signals, unit step response for first order system, and in the second order system, different classification of second order system based on damping factor, as well as unit step response for underdamped second order system we studied in the earlier session. In this session, we will concentrate on unit step response for undamped, overdamped and critically damped second order systems, one by one. Response of undamped second order system for unit step input. Now we will consider the standard form of the overall transfer function of a second order system, which is of the form C of s by R of s equal to omega n square divided by s square plus 2 zeta omega n s plus omega n square. Now we need to find the response for undamped second order system. Undamped second order system means zeta value is 0 or roots are imaginary. Now for undamped system where zeta is equal to 0, then the transfer function becomes, if I substitute zeta value 0 in this expression, we will get C of s by R of s equal to omega n square by s square plus omega n square. So if we equate this, we will get s equal to plus or minus j omega n, which is the complex. Now for unit step input, R of s equal to 1 by s. So what happens to the response in s domain? C of s is 1s R of s into transfer function, that is omega n square divided by s square plus omega n square. If I write this in a partial fraction form, C of s equal to a by s plus b by s square plus omega n square. If we find the partial fraction coefficients, we will get a equal to 1 and b equal to minus s. Then by substituting this a and b values in this expression, so C of s become 1 by s minus s by s square plus omega n square. So if I take the inverse Laplace transform of this, I will get C of t is equal to 1 minus cos omega nt. 1 minus cos omega nt. So when t is equal to 0, cos omega nt is 1. So 1 minus 1 is 0. Okay. When t is equal to pi, then cos omega nt is a maximum and it becomes minus of minus 1 is plus, so 1 plus 1 is 2. So it will oscillate sinusoidally between 0 and 2. So in this case, the system nature sinusoidal will remains there, and so it is called as undamped system. So there is no vanish in the sinusoidal expression waveform. Now next we will concentrate on response of critically damped second order system for unit step input. In the similar fashion, standard form of the overall transfer function of a second order system is C of s by R of s equal to omega n square divided by s square plus 2 zeta omega n s plus omega n square. Now for critically damped, roots are real and repetitive for zeta equal to 1. So if I substitute the zeta equal to 1 in this expression, we will get C of s by R of s equal to omega n square divided by s square plus 2 zeta omega n s plus omega n square. So which is equal to omega n square divided by, this is f of x square when s plus omega n whole square. Now for step input, r of s equal to 1 by s. So c of s response in s domain, c of s equal to 1 by s into omega n square by s plus omega n whole square. So if I write in a partial fraction form, there are three terms. This is the quadratic term, square term. So it is a by s plus b by s plus omega n plus c by s plus omega n whole square. If we solve, we will get the expression for a, b and c as a equal to 1, b equal to -1 and c equal to minus omega n. So in c of s, we can write it as 1 by s minus 1 by s plus omega n minus omega n by s plus omega n whole square. So if I take the Laplace inverse of this expression, I will get c of t equal to 1 minus e to the power minus omega nt minus omega nt e to the power minus omega nt. So 1 minus e to the power omega nt minus omega nt into e to the power, because this is the s plus 1 by s plus omega n whole square. So that is t into e to the power minus omega nt. So omega n is a constant, so this is the expression. So if we substitute the value of t equal to 0, this is becomes 0 because t is 0. This is 1, so 1 minus 1 is 0. So as t increases, 1 minus and so on, as t becomes infinity, this term becomes 0 and it becomes a steady state. So this is the, now this is the t1 where it reaches the steady state value, constant desired output, that is in step 1. Now the response of overdamped second order system for unit step input. Now standard form of transfer function is c of s by r of s equal to omega n square divided by s square plus 2 zeta omega n s plus omega n square. Now for overdamped system, s zeta value is greater than 1, that is roots are real and distinct. Now we can't find what are the values because it depends on zeta and omega n. So I will consider S1 and S2 are as roots. S1 and S2 are as roots. Now based on the roots, we can rewrite this c of s by r of s as omega n square divided by s plus s1 into s plus s2 based on the roots of the equation. Now for unit step input, r of s equal to 1 by s, so c of s is 1 by s into omega n square divided by s plus s1 into s plus s2. So in partial fraction form, a by s plus b by s plus s1 plus c by s plus s2. So I'll calculate only the a because which is a constant 1, and b and c are some expression. So I'll retain this as a constant b and c only. These are the constants, these are not the function of s. So this c of t expression 1 plus b e to the power minus st plus this one. So this is something like this, but only the thing here it is t2 where it is settled down, but this waveform is similar compared to critically damped system, but the difference is this t2 is greater than t1, where t1 is the settling time of critical damp. So that means in case of critically damped system reaches steady state earlier compared to overdamped system. So if I draw collectively, this red colored one is a underdamped system with some value of zeta. Green as well as blue color are also underdamped, but the only difference is this green reaches the steady state earlier compared to red, whereas the blue reaches earlier than red as well as green. Means as zeta increases, this sinusoidal waveform vanishes quickly. As zeta equal to 0, there won't be any sinusoidal, it is consisting of only exponential waveform. And this light blue and yellow, these are the case for zeta greater than 1 or overdamped system. So, to design a controller, we need to concentrate on this waveform. So, some of the terms in this waveform like peak value and the time corresponding to peak, time required to reach steady state at first instance, these are the things which decides the controller, design of the controller. So these factors are called as time domain specifications, so which we will study in the next session.